Well, before I introduce our speaker, I want to tell you how I got to know him and how he came to Langley. I realize many in the room already know him, but perhaps people online do not. In the 1980s, I was working in the vehicle analysis branch, and Del Freeman over here was our branch chief. Del told me a story relatively recently about how he got to know Bobby. Said he'd been on a long road trip, came back and had a stack of mail that tall. And in that stack was this letter from a guy from Penn State University wanting some information on planetary entry that he could use to help him in his senior design project. Well, Dell said at the time, of course, we didn't do planetary entry, but we had a whole stack of papers on Earth entry. So he grabbed up a stack about 10 inches tall, about 6 inches tall, handed them to Cindy, who was the secretary at the time, and said, send them to this guy and see what he can do with them. Well, Bobby did a lot with them. First of all, he got an A in the senior design project. That's an important thing, right? And then he got hired here at Langley as a part of our branch. When he came, he was tutored by people like Dick Powell, Dr. Gerald Wahlberg, and Dell, among others. And he was a busy guy. He rather quickly got his master's degree from George Washington University, and then he was off to Stanford University for his PhD. When he came back, he was working with JPL on a new Mars lander called Pathfinder. Well, it didn't take Bobby long to tap into the historical records that we have from Langley's involvement with Viking, and to pull that information together with the capabilities and tools that were already in the branch. And he developed the first planetary, the first EDL, entry, descent, and landing team at Langley for the Pathfinder mission. That is a program that continues to this day at Langley. A tradition, I should say, that continues to this day with all successful missions, according to Dick Powell, that have occurred on Mars, having gone through Langley. After that, he left NASA and us for Georgia Tech to teach. It wasn't long after that. He was then back at NASA headquarters, where he served as the first NASA chief technologist in more than a decade. In this capacity, he was responsible for developing NASA technology and innovation policy and programs. He carried and led the initial implementation of a spectrum of NASA technology programs designed to build the capabilities required of our nation's future space missions. The activities spanned all 10 NASA centers, industry, and academia, and fostered partnerships between NASA and the other government agencies. From there, I think he took a little siesta back to Georgia Tech, and after a period of time there, a respectable period, he moved on to the University of Colorado at Boulder, where he was the Dean of Engineering and Applied Sciences for 3 years. And from there to JPL in January of 2020, where he became the Director of Planetary Sciences for the Jet Propulsion Laboratory. He currently serves on the executive leadership team of the Johns Hopkins Applied Physics Laboratory as head of the space exploration sector. Bobby has more than 35 years experience as a space systems engineer, technologist, and organization leader. He contributed to the formation, development, and operation of multiple spaceflight missions and is a recognized authority in hypersonics technology and the development of entry, descent, and landing systems. He has served as a tenured professor at Georgia Tech, University of Colorado at Boulder, and Caltech. And in addition, he's a member of the National Academy of Engineering, a fellow in the AIAA and the AAS, and the author of, or co-author of, more than 300 technical publications. It's quite accomplished. Well, Del, I think Bobby's done a lot with that 6-inch stack of papers that you gave him back in 35 years ago. So today he will be speaking on advancements in the robotic exploration of our solar system based on his experience as an organizational leader at JPL during the Perseverance development and landing on Mars, as well as his recent insights he obtained in his current role as the head of the Johns Hopkins Applied Physics Laboratory and Space Exploration Sector. So with that, let me turn it over to Dr. Bobby Braun.
Thank you, Doug. Appreciate that intro. Thank you all for being here. One thing I want to say real quick about that intro, you don't know what it's like when you're, or maybe you do, think back to when you were in college and you go to the mailbox. And not only do you get it's not a letter, but you get this thick envelope of stuff from NASA Langley, mailed to you. I mean, you're an engineering student. It's like a dream come true. It's like, Christmas, 365 days of the year or something. And I'll tell you what, I was the envy of that entire class because I got all that material from NASA Langley. I did get an A on that project. It was one of the few A's I got my senior year. So I remember it well. But yes, I don't know. I mean, thank you for sending me those materials, all those years ago. I appreciate it. I appreciate it then and I appreciate it now. Maybe at the break.
Your request came in as I just come back from JSC at a laser rescue vehicle meeting. That was the material that
That was a leftover material. Well, I tell you, it helped a lot up there at Penn State. So anyway, I want to talk today, typically I give talks about entry, descent, and landing, and I talk about all the engineering technology that I or people around the country are working on in various capacities, and about how challenging it is to land on various bodies. But today I wanted to talk a little bit differently. I wanted to talk about what motivated me and what motivates a lot of people I know to do this work. And there are fundamental scientific questions, fundamental human questions that I think we all have asked ourselves at various times in our lives. When you think back to maybe when you were a Boy Scout or a Girl Scout and you saw that night sky and all those stars out there, and you just couldn't help but wonder, what else was out there? Is anything out there? And for most, I'm not a scientist. I'm going to talk a little bit about science today, but I don't want you to think I'm a scientist. I'm an engineer, and I'm proud to be an engineer. But for most of my life, I've worked on engineering systems that have enabled the expansion of scientific knowledge. And there's been nothing better, as far as I'm concerned, than doing that. And for me personally, the quest that kind of keeps me motivated and keeps me thinking is this question, are we alone? And the reason I'm raising this topic, here at the outstart of my talk is that there's a lot going on in this search today. There's a lot going to be happening over the next decade. And we are better positioned today and in the coming decade or two to answer that question than one could even imagine. Let's see here. I think I'll just use this guy. Ugh, no.
Okay.
Do this. Do this.
Right here.
Right there. Thank you. So what I'm really talking about is astrobiology. And astrobiology is the study of life in the universe. And today there are thousands of scientists across the world that are dedicating their lives to this study. It's something that, frankly, that scientists have been studying for a long time, even before we had a formal definition of astrobiology. When I think of astrobiology today, I think of questions like we're on Mars today and we're talking about, past environments and were they habitable? We're talking about going out to Titan, and Titan is a place where we know that there's prebiotic chemistry, the chemical building blocks for life that existed most likely on the Earth before there was life, exist today on a moon of Saturn, and they're there for us to explore, for us to understand, and for us to, frankly, sample. And then signs of life themselves, right? DNA, RNA, movement. That is certainly the most explicit way to identify life. And astrobiologists are growing in numbers. In the latest Planetary Science and Astrobiology, it's now called Planetary Science and Astrobiology Decadal Survey, there was a very large influx of younger scientists involved in that decadal survey. And many of those young scientists were in the field of astrobiology. So this is a field that's growing in our nation and around the world. Now, I would be remiss if I didn't mention that the first spark that I had personally in space exploration was the Viking 1 lander. I grew up in Maryland, not far from where I'm living today. And down the street from me, there was a NASA employee. He later became the chief engineer at the Goddard Space Flight Center. His name was Dick Freeman. And when Viking was landing, for some reason, he decided to bring me into Goddard. And I got to watch that landing on screen in Goddard, and I got to watch the scientists and engineers celebrate that landing, like only, engineers can, like a little high five action, where they, eventually they get it right. And the reason I'm talking about Viking is it was a spark for me as a young child, but it was also, I would argue, the first astrobiology mission. It wasn't called that at the time because no one used the terms astrobiology. And Viking did a lot of good science, a lot of good technology, engineering work, of course, led here at the Langley Research Center. But one thing that Viking, really tried to do is it tried to hit a home run in the search for life by going to a place that we hadn't reconned in advance, by a place that we didn't have great images from orbit, landing safely. Viking 1 and Viking 2 landed safely twice, but they landed in these barren, dry rock fields. And while there was a life detection experiment on the Viking 1 and 2 landers, its results were inconclusive. And as a result, and partially because of the hype surrounding the search for life in Viking and the inconclusive findings, the images that were shown, we didn't go back to Mars for 20 years. I think there's probably a number of reasons why that occurred, but I feel that that's a huge miss on NASA's part in those decades. I have no idea why we stopped, going to Mars. But we did go back. And in fact, as Doug mentioned, I was employed here at the NASA Langley Research Center in the 90s and got to be involved, along with Gary Qualls, who's sitting over here, and a handful of other people here at Langley. Got to be involved from kind of the concept through the flight for the Mars Pathfinder mission. Pathfinder landed on July 4th, 1997. It was the U.S.'s first rover mission to another world. The Sojourner rover, took off, and you could say the age of mobility on planetary surfaces began. What I like to point out is not only was Mars Pathfinder successful, but it and Mars Global Surveyor ushered in an era of continuous U.S. presence at Mars since that time, right? A very different result than, the legacy, if you will, of Viking. So why is that? I would contend that that's because we took a different view to our exploration of Mars. It wasn't about finding life. It was about understanding Mars as a system. Life was one of the reasons that we would explore Mars scientifically, but understanding the past climate, the geologic conditions and how they changed over time, understanding whether Mars was a place where humans could one day live, work, and play, were all goals of the nascent Mars program in the late 90s. And that program has continued with a whole series of rovers and orbiters, and most recently a helicopter, exploring the Mars surface. And for me, having been part of Pathfinder, getting to watch this evolution and advancement in technological capability on Mars and see the scientific results that have come back, to be honest, it's more rewarding to see the 20 years of science than just the landing itself of Pathfinder. And it's something that I take great pride in. Now, of course, when we go to Mars, we understand Mars as a world. What we're really doing is we're looking into the past of the Earth. We're learning about our own planet. Mars does not have magnetic fields like we have on Earth. It doesn't have major earthquakes or plate tectonics. It doesn't have a surface today that's covered with water. So, when you're looking at Mars, you're looking at a planetary body that's kind of not frozen, but reminiscent of what the Earth might have been in the past, right? We don't have the plate tectonics changing our surface as we do on the Earth, or other conditions that are affecting Mars in the same way. So that's another reason that we explore Mars. And most recently, out at JPL, I was involved in the Perseverance landing. This was just a year ago or so, a little more than a year ago. And the Perseverance landing, of course, was a culmination, like all these projects are, of 8-10 years of people's sweat and work and worry. And so being the executive at JPL, responsible for the team that was doing this work during the landing itself, having gone from doing the work on Pathfinder to being in that role during the Perseverance landing was just, a remarkable thing. In fact, many of my former students from Georgia Tech or from CU Boulder were actually doing the role, very similar role that I had done on Pathfinder. And that was also kind of a really neat thing to see. So I wanted to share this video with you, hopefully. I'm going to share this video. There we go. Just to kind of remind you of what it was like on February 18th, 2021.
We have deemed Perseverance ready to execute entry, descent, and landing on our own. Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute is deployed, and we're seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The backbone has separated. 5 meters ahead of target, or 20 meters off the target. Confirmed. Perseverance. Yeah.
Yeah. So 10 years of people's lives, a much more capable rover, much more capable EDL system than anything we had done before. By the way, there are many more people here at Langley who are involved in Perseverance than Pathfinder. The team at Langley that's contributed to these things has grown over time as well. I just want to say that the folks that did this, they're true heroes. Imagine doing all that technical work during the time of COVID. Right? I mean, obviously, a lot of it was done before COVID, but I can tell you, we weren't ready to go when COVID hit. And my biggest fear in that time frame was, where are we going to make launch? Because of all the things that still had to happen in California, in Florida, at other facilities around the country, in the early stages of COVID, before there was a vaccine, right? When people who were traveling or working in Florida, away from their families and wanted to fly home, and they were taking real risk, not just for themselves, but for their families. These people did a tremendous job and a tremendous service to our nation. So Pathfinder, Spirit, Opportunity, Curiosity, Perseverance. 5 rovers in 20 years. That's quite a feat for the United States of America. And 1 helicopter. Ingenuity. And in fact, in some of our darkest moments during the COVID pandemic, this landing, I think, brought us together. Whether it was the lighting of cities that were red all around the world, or newspaper headlines. The president called the control room within 30 minutes of the landing to congratulate the team. He talked to Steve Jerzik, by the way, who at that time was the acting administrator. He later called back and talked to a whole broad swath of the team. He's very good in those kinds of interactions, by the way. It was great. This was huge. This was a big deal. Now, it was a big deal for the science of the mission itself, but more importantly, this rover ushers in the age of Mars sample return. And I can remember back to the time that I was here at Langley and I gave a colloquium and I said something like, Mars sample return is going to happen this decade. And I was wrong. But really, Mars sample return is going to happen this decade. I know it. And the reason I know it is because it's already begun. Perseverance, as it traverses across the Mars surface, is actually collecting, sealing, and will place in a cache samples that are scientifically collected that will be a treasure trove and which we will go back and return. And so the very act of collecting these samples, I would say, is the beginning of Mars sample return. And in these next 5 or 6 years, not only is Perseverance going to be doing that across the Mars surface, but here in this country, we're going to be building the flight systems that are going to go get those samples. Another lander, this time one that for the first time will know exactly where it wants to go because the samples are going to be like a big X, right? Land right next to the samples. An ascent vehicle, 2-stage rocket that'll lift those samples into orbit. An orbiter and an Earth return vehicle, much like the early concepts of that Earth return vehicle that was designed right here at NASA Langley in the late 90s. And that Earth return vehicle will bring those samples back to Mars. Present time frame is that the next set of missions will launch in 2028 and the samples will be back in 2033. But sample return is happening right now. In fact, these are some images from some of the early rocks that have been cored across the surface of Mars. We've now cored and acquired 15. Not rock. We've sealed 15 rock of our sample tubes. 12 of them with rock cores in them, 1 with an atmospheric sample, and 2 witness tubes that we brought with us. That's how we measure contamination over time. If there is any. So we have 15 sealed tubes, and Perseverance is carrying 43 tubes. We're headed towards the rim of the crater in which we landed. And we're going to place some number of those tubes. It depends who you ask how many. I mean, it'll be more than 10, I would guess, on the Mars surface before Perseverance continues its journey up that crater rim and eventually to the next geologic region where it's going to continue its exploration for a number of years. It's going to gather more samples in those regions. And depending how it goes, it may place another surface cache. It may hold on to those samples. It may bring them back to the original location of the cache. All of that is just operational dependent, right? Depending on the risk to the rover. The primary path for the return of the samples is that Perseverance will be alive, much like Curiosity is today. Curiosity is 10 years old as it travels across the Mars surface in a different region of Mars. So the primary path is that Perseverance will bring samples back to that lander, and they'll then begin the journey home. The most important thing, though, is that we have a diverse set of samples because we're trying at Mars to answer a diverse range of questions. Questions of habitability, questions of the potential for life are just one of many questions that we're addressing at Mars. So this is an image that I just love because it just points to the progress that we've made on Mars over the years. We know today that Mars is a remarkably diverse world. It's a world that actually continues to teach us new things, not just about itself, but about our home planet. And we're entering this new era called sample return, which I believe will be among the most significant planetary science undertakings that our world will ever do in planetary science. And when I say our world, I should point out this is something that NASA is doing in partnership with our friends at the European Space Agency. Mars Sample Return is, of course, a round-trip mission over multiple launches. It's a round-trip mission. And so, in a way, it's also a pathfinder for eventual human exploration. Now, while that's going on, there's a whole other theme to planetary science that I wanted to touch on here today. And that's the idea of exploring the ocean worlds in our solar system. Now, when you view the Earth from space, you see a big blue marble, and you think of the Earth as encrusted with water. But if you look out across the solar system, Enceladus is hiding in this picture. If you look out across the solar system, these little blue circles indicate how much water is available at each of these bodies. So you can see how much water is available in Earth in the size of that circle on the left-hand side of the screen. We believe that at Europa, one of the moons of Jupiter, there's something like 2 to 4 times as much water beneath its ice-encrusted surface. At Titan, something like 14 times as much water. And at Enceladus, which is another moon of Saturn, both Titan and Enceladus are moons of Saturn, Enceladus has less water, most likely, because of its size, on the order of about 1% of what is available to us here on the Earth. But the point is that there's water on these worlds. And we also know that because, not just of the sun, because of the gravitational attraction and oscillation as the moons move about their host planets, there's energy generated. So there's water and energy. Well, where else is there water and energy? This is a video that I'm sure you've seen. Comes from NOAA. And it's a video of the hydrothermal vents on the deep sea floor here at the Earth. There are many theories for how life began here on the Earth, but one of the most prevalent is that they began deep in the oceans at hydrothermal vents where there was water and energy, and where today there's still a host of life. And so I'm not stating that the same is true in these other worlds, but it does give you pause. It does make you think, if there's water and energy in these other worlds, what are we going to find when we go there? And the good news is that we're going there. We may find nothing. but we're going. We're going to Europa. We're going to Titan. And one day soon, we're going to be going to Enceladus as well. So we're going to Europa with Europa Clipper, which is a huge orbiter under construction at the Jet Propulsion Laboratory right now. It will be launching, hang on a second, there it is. It'll be launching in 2024. And it is right now the largest mission in the planetary science portfolio that's being worked on. People are working on it all across the country. People at APL have had a big role, at JPL, at universities. And in fact, there was a test just recently here at Langley of the RF antenna that's going to be used by this huge spacecraft. To give you a sense of of where Europa Clipper is, it's in the hardware development phase today. The hardware is being finalized. Everything's being shipped to California on various timelines because it's at JPL where the spacecraft will be integrated. For nearly the final time. It'll then be shipped to Florida for preparations for launch in 2024. It's a fantastic mission. And one of the reasons it's so interesting is because Europa is known to contain liquid water, to have an interesting host of chemistry, chemical ingredients, potentially for life. And there's energy sources. In fact, we see that with the plumes across Europa today. So there's chemistry available. There's questions about how does the surface alter those materials? How does it allow transport from the deep subsystem, from the deep ocean up near the surface to the water-ice boundary, and through that ice boundary onto the surface? It's an orbiter, so we won't be touching that world, so to speak. But we are carrying a number of sophisticated instruments that will tell us things about the depth of the ocean. There's a mass spectrometer on board that may allow us to fly through some of the particles that are hoisted by the plumes of Europa. It's going to be a fantastic scientific voyage. And depending what Clipper uncovers, there could be a lander in Europa's future. We'll see. There's not one planned currently today, but we'll see where that goes. The next world that is also a target of exploration today is Titan. Titan's the moon of Saturn.
I have to bother you. I'm sorry. Could you tell me where to find the right age number? I'm calling them. It's almost 1 o'clock.
What's that?
Yesterday.
It's on the prescription bottle.
I just looked on one that you have on your table and it's not there.
It's up.
What was it? I don't know. Yeah, that's okay. So we're exploring Titan today, or planning to, with a mission called Dragonfly. And Dragonfly is being led out of the Applied Physics Laboratory, but also involves some researchers and work here at NASA Langley, and frankly, around the country. Dragonfly is going to send, they like to refer to it as a lander. I don't know why we actually do that. I think it's a drone. But it's the first relocatable lander to explore Titan's surface. And remember, Titan is the home of prebiotic chemistry. So it's really a place to go to explore, what you might find with your chemistry set. Here are some Cassini and Huygens images of Titan relative to similar images of the Earth. Titan is a home of lakes and seas, of impact craters, of sand dunes, of potential riverbeds, not rivers of water, but rivers of methane, methane and ethane. But still, just look at the comparison, really, of Titan and the Earth in these images. If you were viewing both planets from space, you might, from this kind of evidence, you might have a hard time distinguishing the two. And the chemistry at Titan is fantastic. There are known to be complex organics in Titan's atmosphere. They were measured by the Huygens probe. that flew along with Cassini and did a descent through that atmosphere. We don't know how the atmospheric constituents interact with the surface, either chemically or how they physically modify the surface. We know that there's a subsurface ocean of water on Titan, but we don't know today how that subsurface ocean interacts with the surface, which interacts with the atmosphere. So there are a hodgepodge, a plethora of questions scientifically about the exploration of Titan. And if there was one world that we could go to study life, it would be Titan. It's probably, I mean, I like studying all these worlds because the diversity helps answer the large questions. But if there was one world that you would want to go to address this question in our solar system, I think exploration of Titan would be it. And it's also, unlike Mars and our own moon, it's a pretty hard world to reach. So this mission is in development right now. It's in the preliminary design stages. Later this decade, it'll be set up for launch, probably in 2027. It'll take us about 7 years to get out to Saturn and do a direct entry at Titan. We refer to it as entry, descent, and landing, but it's really entry, descent, and deployment, because while we're descending on the parachute, the lander will come out of the parachute and begin its first flight, finding its safe location to land. So unlike Mars, where we have all kinds of orbital imagery and we know ahead of time, this place is safe, you can land here, don't land over here. This lander is going to have to find a safe zone, as it descends to Titan for the first time, because we just don't have the recon available. The lander itself is mobile through flight. It's powered by an RTG, and it is loaded with scientific instrumentation, including all kinds of cameras and spectrometers, imaging spectrometers and mass spectrometers to do that chemical analysis. In fact, here's a little video of what that descent might look like once it's gone subsonic on the parachute. The lander comes out of the back shell and searches for a safe location. We are targeting a region on Titan that we believe to be safe because we have mobility, but we haven't been able to see the surface at the scale of the lander. By the way, this lander is huge. It's the same size as Perseverance. It's the size of a small car. Okay, so this is not, the drone that you go buy at Toys R Us or whatever, get for your kid. This is a serious drone that's very capable, and it has direct-to-earth communications. It largely has to operate autonomously. Once it takes imagery of the foreground that it uses to find the next safe landing site as it lands at the first spot, and then it uses that to kind of hop across the Titan surface. And in fact, in that way, over many years, something like 3 Earth years, it'll traverse a couple 100 kilometers, 180 kilometers or so, and it'll land in 25 to 30 locations, some of which are cratered locations, some of which are dunes, and some of which are thought to be ancient riverbeds or lake beds. So it's going to traverse a broad range of geologic constituents as it takes its chemical measurements across the Titan surface. The last world I want to mention is Enceladus, and only because Enceladus is a place that is spewing water into the solar system today. The tidal forces are so significant that subsurface water is coming up through the surface and going out in space. And so you can sample the Enceladus water from orbit. There's thoughts that this same kind of phenomenon will be true at Europa, but there's much more evidence of it, even though there's less water. There's more evidence of it today at Enceladus from Cassini. And this is just a graphic to kind of depict what that looks like. The water is coming up from above the core, but between the core and the crust. It's it's thought to be an ocean, and the gravitational forces are causing that water to escape, carrying with it whatever constituents are there. So, if there are organics or other complex compounds in that water, they're being carried out into space. One of the challenges with just flying through is that you have to do so at an extremely high velocity. And so capturing that water or those constituents in space at high velocity, you're worried about modifying them. So a better idea, certainly that's a lower cost alternative, but a better idea would be to simply land on Enceladus and have it rain down on you, if you will. And that concept is called the Enceladus Orbilander, and it was one of the studies that was highly prioritized by this most recent Planetary Science and Astrobiology Decadal Survey that came out last few months. In fact, in terms of flagship missions, which are the large missions that NASA is going to pursue, this was the number 2 mission behind a Uranus orbiter and probe. And so should the decadal prove to be accurate, and you never really know if these planning documents are going to be accurate, but the planetary science community has a pretty good track record if you look at past decadals. This mission would occur in the 2030s. Okay. So imagine both an orbiter that's perhaps flying through the plumes and a lander that is being rained upon out on this amazing moon of Saturn. I can see it now. It'll be glorious. So, I wanted to touch on astrobiology. It's a growing field. It's an amazing field that is growing in the diversity of folks across the country that are interested in it. It's a field, in my view, whose time has come. The work that's going on in laboratories around the country right now, in instrumentation, in the engineering systems required to support those instruments, is really enabling one-of-a-kind, first-of-a-kind missions that are going to allow us to answer fundamental questions like, is there life out there, in a way that, frankly, we couldn't do in the 70s with Viking. I believe the potential for astrobiology is almost unbounded, and the technology advances of just the last few years are about to unleash this field in the planetary science domain. NASA today has plans to return samples from Mars by the early 2030s and visit many of our solar systems, at least 3 of our solar systems' ocean worlds in that same time frame. If you had told me that when I was starting at NASA Langley in the 1980s, I'd have been like, sign me up. That is exactly why I wanted to be an aerospace engineer. To get to work with people across the country on big challenges like this, scientists and engineers working together, trying to hammer these things out. I've been very blessed in the missions I've been able to be a part of in my career. And I can think of no better way to apply my energies, for the remainder of the time that I'm working in these kind of fields. And after that, I'm sure I'll be watching. Now, the other thing to think about is how the questions themselves have changed. When I, first started working in the Mars program, the question was really about water, right? We're going to follow the water. That was the theme that we all talked about. Was there water on Mars in its past? Today, we know that answer. The answer is yes. There is an abundance of water on Mars in its past. There's all kinds of evidence that points to that. And so as we proceeded along that quest, the question changed a little bit. Well, there was water, but was there chemistry? The chemical constituents of life? And we know the answer to that today, too. The answer is yes. There was a lot of chemistry at Mars. And so today we ask questions about habitability. And that's really what both curiosity and perseverance are all about. Was Mars habitable in its past? And I believe the answer to that will also be yes. But that doesn't mean there was life. And, you know, the samples may tell us that. But I also think it's possible that Mars isn't the right place to be looking. Because it's a fairly inhospitable world. It's not an ocean world. And there are ocean worlds in our backyard. And so I'm all for Mars sample return, and I'm all for Mars exploration. I'm also for the exploration of the ocean worlds in our own backyard. Worlds that we know have an abundance of water today, some of which have prebiotic chemistry, and have abundant energy sources for life. And so I'm super excited that not only are we exploring Mars, but we're going to explore some of these other worlds as well. And I can't wait to see what we learn. Thank you for your attention. I'm happy to address any questions you may have. Thank you.
Doug, were you going to read the question? Well, we can entertain about 3 questions from
Great.
here, and then we like to, well, and then we like
That's
to
fine.
switch to several questions from the online audience. And then, so, how did we go on?
Thank you so much for this great help and seeing your energy results in situation.
It's nice to see you as well. Yeah, I don't know how to change that. I've tried.
So I have a question and my question is about, you explained a lot about Mars and what I completely see what you said. It has been great engineering achievement.
Mm-hmm.
That of engineers. It's a great engineering achievement. It looks like the science is starting. And some things have been found out, and definitely we have to read this morning, inspired by your talk, when the samples coming back. And I was a little bit astonished, they're not coming back. I didn't know that.
Yeah.
But it is still in the very span of time. I think, like you're saying, a lot more will be known. So I am excited about knowing the science of what we have done today. So that is my question. I did not know much about it for explaining other planets and various types of water. Like the question for about Mars is, other than knowing that probably some kind of water existed before in some form, what else have we found out? The scientific truths about Mars.
Well, that's going to take a lot longer to answer. What I didn't touch on was all the orbiters that have been flying at Mars since Mars Global Surveyor. And to be honest with you, a majority of the science that we've gained on Mars comes from the orbiters, just in terms of data volume. So, Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, the Europeans have an orbiter. There's an orbiter called MAVEN. And they each have a broad set of science objectives that range from, understanding climate, to understanding what happened to the Mars atmosphere. It used to be much thicker at Mars than it is today, and it's been stripped away by the solar wind over time. The MAVEN mission, for instance, has focused on that aspect. In terms of the Mars surface, we've learned about the age of the surface, from crater counts and the chemical constituents of various regions. I mean, it varies over the surface significantly, and that's allowed us to direct landers to various spots of interest, based not just on geology, what it looks like from space, but also based on chemistry. So there's been, I would say, scientific advancements in I mean, more fields than I can count through the Mars exploration program. Just as one example, Curiosity, which I mentioned, has been troving across the surface for a decade now. I think there's close to 1,000 journal articles from the Curiosity science team on the trek that Curiosity has made across the surface and what they've learned about the geology and the geochemistry, and largely the past, if you will, of that surface.
It's our own planet,
Mm-hmm.
our fault. So, as we all know, what we're on.
Mm-hmm.
And I'm wondering how all the great work NASA has done, understanding other planets, should give us, not just as the board, more appreciation for the planet we live on.
It should.
Yes, that is my comment and concern. We are called Goldilocks planet. And why can't we pick that planet as we understand more? Could NASA do something with messaging in that?
NASA certainly could. I don't speak for NASA. I will say that, while I've spent the bulk of my career studying, designing systems to explore Mars and the planets, the Earth is still my favorite planet. Everybody I know and everybody I love lives on the Earth. It's the only place you can get a good pizza. And these things are important to me. But no, in all seriousness, I think that NASA could do a lot more to talk about the fragile nature of life on the Earth from the vantage point of space. I mean, you don't have to go to look at Venus and Mars to see that. Just look down from the International Space Station or even from the suborbital rockets that are flying today. People come down with a very different view of the fragility of our ecosphere. So yeah, perhaps the commercial space industry will actually help with that as well. Yeah, it's a good question. Thank you.
I was going to ask you a quick question about you. So, a couple of years ago, I heard a presentation from Canada University. They talked about Europe.
Yeah.
Just like you said, today, there were much more possibilities than the exploration to Europe. So, what is the reason, from the higher level strategic perspective, that we have not put the resources into the
So Europa is a really intriguing target. Absolutely. And we're going, right? Europa Clipper is launching in 2024 for Europa. It's in development now. But if you're asking why we haven't landed on the surface, it's because we need to do the recon from orbit to design, in my view, to design a safe lander, to actually go to the right spot, right? We didn't do that work for Viking, by the way. But, to pick just the right spot before landing. Now, there's technology program going on today to get ready for a lander to Europa. But my view is, you have to do these things in pace, and you've got to get the scientific results have to come back from Europa Clipper to inform the design of the Europa lander. Right. One of the reasons that we have so many missions that go to Mars is because we can. Once every 26 months, Earth and Mars line up, and there's a convenient time to go. And it takes like 7 months to get there, which, kids will say is a long time, but you and I both know that 7 months is a blip, right? It takes 7 years to get to Europa, right? And you can go every year, you can launch every year, but it takes 7 years to get there. And so it's harder to build a program around Europa. Now, if you think about ocean worlds, you can send an orbiter to Europa at the same time you're sending a mobile lander to Titan, Then you can come back to Europa, and then you come back to Titan. You can do something like that. And that's what I think NASA's trying to do, is think about the ocean worlds as a target, in a sense, just like Mars is a target. And we have a series of orbital and landed missions to Mars. We should have a series of orbital and landed missions to the ocean worlds. It's a good question. Thank you.
Given the time, I guess we need to try to end off with some to see if there are online questions.
Mike, any online questions?
Mike asked me to fill in for him. The first thing I would say is that we have a difficult time remotely hearing anyone at the table. We basically can just hear the speaker, and if you try really hard, you can barely hear anything. So I was even wondering if I could hear you ask if we have questions. Anyway, we do have some questions, and I will repeat them. The first question is about exoplanets, and that's from Kiyomai Duta. He says, what about the exoplanets? Tell us some of your thoughts about exploring them.
Love the exoplanets. So, yeah, I actually debated whether I should have included that in this talk. So if you think back to, the time frame in which I began my career, for instance, at NASA Langley, I'd look up in the night sky and I'd see all those stars, and I knew there were planets around some of the stars, but I had no proof. And today, we know not about 10 or 100, but we know about tens of thousands of worlds around other stars. And the James Webb Space Telescope is going to just blow our socks off with its measurements of exoplanets. Now, most of the exoplanets that we know about today are Uranus or Neptune-sized exoplanets. So that's also part of the reason why the Planetary Science and Astrobiology Decadal Survey is interested in exploring Uranus and sending an orbiter and probe to Uranus in the late 20s, early 30s. It's because if you were outside our solar system and looking at it, you would most likely notice Uranus and Neptune first, like we do in exoplanets. Now, we now know that there's a large number of exoplanets, but what really excites me is just the technology that's coming online with Webb. The results haven't come in yet, but there's going to be, we'll be able to do atmospheric characterization of some of the exoplanets. There are technologies in development to do, water type characterization of the exoplanets. And so, today we talk about, an Earth-like exoplanet as being one that has approximately the right temperature, because it's the right distance from its host star, depending on the energy of that star and the distance of the planet. So it's in that Goldilocks zone that was referred to earlier for the Earth. But, a few years from now, we'll refer to an Earth-like exoplanet as one that's the right temperature and has maybe the right atmosphere and maybe has some water content that we can see. A few years later, we'll look for trace pollutants in that atmosphere. As a bit of a joke, but maybe not. I mean, that's the way our technology is going. You should definitely be following astrobiology, but exoplanet science is also something that's just off the hook in terms of its growth potential. Great question, thank you.
Yes, the last question that we have is regarding you yourself, and that's a question I have. Last year, Dan Palumbo was setting up the agenda, and he had something about life after NASA. So I'm curious about how you would compare your life after NASA at the Applied Physics Lab. I've been there and visited, and it seems like a pretty exciting place, but on the other hand, Langley and NASA are too. So and I guess to make it easy for you, what about things like the competency of the people, comparing them, the leadership, the drive, and you know, some of those kind of things you might have comments on.
Yeah, sure. I'm happy to address that. So, first of all, you know, I just want to say a couple things, which is that I've had a lot of chapters in my life after NASA, right? I was at, you know, multiple universities, for example, you know, including at JPL, which is not really NASA, to be honest, and now at the Applied Physics Lab. I found all of those experiences to be great. You know, I'm very, you know, you learn something at every place. You meet interesting people and exciting people at every place, and you're just constantly learning. But to be honest, I was happy to accept the invitation to come back here. You know, I accepted, by the way, when I was still living in California. I accepted the invitation to come back here because Langley means a lot to me. This is where, for me, my career started. This is where my formative professional years were. And in fact, I believe that almost everything that I've done is really largely a result of the people that were around me in the vehicle analysis branch and elsewhere that mentored me and kind of pushed me along and encouraged me, you know, to ask questions. I think I showed up at Langley kind of quiet, and I left Langley pretty loud. So, you know, I would attribute much of my success, whatever success I've had in my career, a lot of it to those formative years and mentors that I was extremely fortunate to have, mentors and friends that I was extremely fortunate to have here at Langley. Touching on APL for a second, APL is a wonderful place. I love it there. My father worked there for 35 years, so for me to, you know, work there towards the end of my career, there's even a few people there who remember my father. So it's kind of like going home again, even though I never worked at APL as a kid. The place is extremely technically focused. Every decision, you know, everything's technical. It's very different than my late NASA experience, you know, which was, you know, a lot of budgets and workforce and, you know, facilities. When I was at headquarters, I'm referring to, kind of focus. The science and technology staff at APL is extremely strong. It's a place that knows its mission. They know why they exist. They exist to serve our nation, whether that's the Defense Department or Homeland Security or the intelligence community or NASA or what have you. And they don't compete with industry. They don't compete with government. They do work when asked by various government sponsors. And for me personally, that sense of national service is very important. You know, it's something I resonate with, and I haven't felt that way in a long time. Like, I felt that way at Langley. But, you know, when you're out working in industry or in a university setting, it's a different motivation, right? It's about giving back to the next generation or creating, you know, new systems. In industry, it's about, you know, profit, for example. But, you know, at a lab like the Johns Hopkins Applied Physics Lab, it's all about national service. And you feel it when you walk across that campus every day. Thank you for that question.
Well, thank you very much, and you did a wonderful job. I heard your NC State talk, and I'm an NC State alumnus too. I'm proud of you.
Thanks.
Thank you, Ola. Thank you. And oh, that's great. Please accept this.
I will. Yeah. Absolutely. Thank you very much.
Gratitude. There you go. Thank you, Bobby. That was great.